Hello, I'm Adam Chapala, one of the programming committee members for POPL, and it was my pleasure to introduce our final invited speaker of the conference. Unfortunately, due to a technical glitch, we lost the first few minutes of the recording, so instead you'll be treated to this historical reenactment of my introduction, which was for Joe Hellerstein, who works in the area of databases, which has lots of interesting overlap with programming languages and compilers, to the point where I'm always surprised that there are so few people who are active in both communities. Joe is a professor at UC Berkeley, where he's accumulated the usual academic honors like being an ACM fellow, but he's also active in entrepreneurship as co-founder of Trifacta, a startup whose product makes it easier to combine large amounts of data from different sources. We can get a sense for Joe's research contributions over the years by looking at his 3 different papers that have won Test of Time awards from SIGMOD, one of the top database conferences. So these include optimizing database queries using a rewriting engine, improving the user experience for summarizing large amounts of data in a database, and executing queries in wireless sensor networks. I listed those in chronological order, and I think one developing theme that we see is moving from problems that apply to a single database server to handling the increasing complexities of distributing query execution through time and space. And the talk he gives expands on that theme further by dealing with distributed systems on the internet. Without further ado, over to you, Joe.
Hi, I'm Joe Hellerstein. Thanks for inviting me to speak at POPL this year. I'll be talking about the programmable cloud, foundations work that we've been doing in our community, and challenges that lie ahead. We have this saying in computing that with every new platform comes a programming environment that unlocks the potential of the platform in ways we never would have expected. And this mythology goes back in the systems community, at least to the Turing Award-winning work of Ritchie and Thompson on Unix and C on mini computers, and arguably rolls forward through multiple generations to current environments like smartphones and the public cloud. Surprisingly, though, a programming model for the cloud has yet to emerge. We really don't yet have a native programming environment for the biggest computer ever assembled by humankind. And so, from my perspective, one of the grand challenges, if not the grand challenge in core computer science right now, is how to unlock the potential of this unprecedented platform in ways that will allow third-party programmers to do things we never would have expected. I'm going to come at this problem from my perspective in database systems and logic programming. Now, arguably, there's good reason to look at cloud programming through this lens. Famously, the relational model is built on relations, which are an unordered data structure. And so they are a nice fit to the asynchrony and parallelism inherent in the cloud, a very disorderly environment. And yet, despite that disorder, they bring a well-defined semantics. And the database community has been exploiting this since like 1979 when Teradata was first launched, through the 80s research projects like Gamma and Bubba that pioneered the idea of parallel query processing that has rolled forward successfully through generations of parallelism, including the MapReduce frameworks and big data frameworks to modern times. So long tradition of success with parallelism in data-centric computing. Also in the relational model, Codd's Turing Award was famously given for the declarative languages that he specified. And this declarativity, this separation of the what from the how, is so natural in the cloud. It almost seems to be crying out for it. This is a platform that is heterogeneous, it's evolving. And then with modern auto-scaling software, the goal is to have the software, in fact, change its execution model, scaling up, scaling down, possibly changing strategy, dynamically over time while it's running. So the idea that we would write a program that would carefully hardwire all the aspects of execution seems wildly overfit to the potential of this platform. We really want declarative programming that specifies high-level outcomes and allows the cloud to dynamically decide how to execute these outcomes. I hope to convince you today also that this lens on the problem is actually quite beautiful, that there's a lot of nice formalism here. There's a growing body of work on distributed logic programming, building, of course, on foundations in logic programming that are long established. And this work's been causing us to not only answer new questions, but to ask new questions, fundamental questions that had sort of been lurking in the distributed computing literature, but hadn't been asked before. So really an opportunity for the principled pieces of the distributed systems community, the database community, the programming languages community, to put our arms around each other and work on these problems together. Now, in my own group, my prior generation of students that graduated sort of 7 years ago, were involved in a lot of top-down design, starting with languages and runtimes for declarative networking, expanding into more full-featured cloud programs, and then stepping back and asking about those language designs in terms of what are their foundational semantics and what can we prove about programs given those semantics. So a lot of top-down work done, sort of for the period from 2005 to 2012. And then my most recent generation of students graduating now out of the RISE lab have been taking those lessons and building bottom up to build systems, particularly serverless systems, that exploit those lessons to get high performance and auto scaling features. So the ANA key value store is the fastest key value store right now for contended workloads because it takes advantage of lessons from the prior work. And then the Cloudburst stateful functions as a service system is the only functions as a service system today that allows for multi-master update with consistency across these updates. Again, using lessons from the work that we've done foundationally up to now. What's happening now in my group is we're trying to bring the formalisms, the top-down, and the implementation, the bottom-up, together. So we have a paper in CACM just last September reviewing some of the theory. This is the Keeping Calm paper, and the CALM Theorem is going to be a topic of much of the discussion today. And then just last week at CIDR, we had a paper on our directions looking forward in cloud programming. And at the end of today's talk, I'll give you a preview of some of that vision as well. All right, so today is a talk in 4 parts, and we'll begin with this declarative programming lessons learned from our prior generation of students and how it led us to a desire for better formalisms, which we'll go into thereafter. So this work began in an era of peer-to-peer networks when people were searching for files on other people's computers. And the idea of querying to find a file was conflated with the idea of routing the query to a machine that would have the file. And so this connection between routing and querying was emerging through these open source peer-to-peer protocols. And we asked the question more generally, why not look at routing as a query processing problem altogether, for sort of from the roots of routing in the internet. Now, routing itself is like a classic transitive closure problem, and therefore very natural in a language like Datalog, almost canonical. On the left here we have expressed a routing query, but it's really just the classic Datalog transitive closure program. We have a relation link of pairs xy. We declare that if there's a link between xy, there's a path between xy. And then, the canonical transitive closure rule, if there's a link from x to y and a path from y to z, then there's a path from x to z. And given those 3 rules, then you can pose queries like find me all the paths out of S, or find me paths between the pair S and T. And with small modifications, you can turn this into an optimization problem where you calculate the cost of each path, and the query is to find the minimum cost path between S and T. And we did all these things, and we actually built out a distributed runtime for these kinds of queries. And in that runtime, messages would get sent to compute the answers to the queries, and those messages corresponded to routing protocols. And in fact, what was exciting was we found that classical query optimizations on these programs would lead to different routing protocols, which were classic in the networking literature. So one order of joins, for example, would give us a routing protocol called distance vector routing, which is used in internet routing. Another reordering of those joins would give us a protocol called dynamic source routing, which is better suited towards broadcast media and wireless computing. So what we were seeing was that query optimization and protocol synthesis were kind of the same thing. And it really gave us the confidence and maybe the arrogance to think that we could build more and more interesting systems out of these declarative languages and synthesize the protocols and the implementations beneath them using query optimization. So we got ambitious and we started doing things like building distributed hash tables where you're routing not by address, but you're routing by key, right? You say, I would like this message to go to wherever Bob is right now. And Bob has been hashed to some node in the network, and there's a multi-hop routing protocol that takes the name Bob and finds where it currently is in the network. And this is our implementation of Stoica's chord protocol for distributed hash tables in Overlog, which is the routing language or the declarative language for routing we had built at that time. And, it's not terribly readable like a lot of logic programs, but it is one piece of paper. You can print this out, take it to the coffee shop and study it. And the various sort of subroutines here that are commented are readable, certainly more readable than the tens of thousands of lines of C++ that was the implementation from MIT. Okay. We got ambitious from there, though. We decided to build a full backend system. So at the time, Hadoop was extremely popular in the distributed systems community, and we decided to rebuild the Hadoop file system in an API-compatible way so it could really slide in Overlog. And we also gutted the scheduler in Hadoop and replaced it with an Overlog implementation. And we got this working to the point where it was really pretty fast. And as an example of the things we did, we implemented Lamport's famous Paxos protocol for consensus. It was 22 Overlog rules, and it corresponded nearly line for line with the invariants from Lamport's original paper. So not only is logic compact, but in at least some cases, there were other examples we had of this with distributed hash tables. The language seemed to be well fit to the problem. Sort of, we were expressing invariants of what information should be where in the network, and that was precisely kind of the way that these protocols were described in their original papers. So, I'm bragging a bit for sure. Some things worked well. It was concise and declarative, good order of magnitude, more concise than the Java implementation, and performance was competitive. We didn't work super hard to tune our runtime performance. We've done better things since. And it had this nice separation of policy and mechanism that you'd hope to get out of a declarative implementation. And then the thing we really bragged about and enjoyed, so to speak, in the implementation that we talked to the systems community about was the evolvability of this software. So it's really a software engineering benefit. We showed how easy it was to take the critical failings of Google File System and Hadoop as its clone, namely its master, and then it had a model of a head node and a bunch of workers, and that head node was a single point of failure and a single point of scalability bottleneck. And we showed how to make the head node replicated and highly available using Paxos. We showed how to take that master node and, even while it's replicated, partition its state across many nodes so it would scale out. And that work, that second step of scalability, was so easy because all the state of the system, all of it, was in relational tables. It was in these data log predicates. And so it was simply a matter of picking a partitioning key on those tables, and the system suddenly scaled out. And that was work that was done in a day by a student who wasn't even in our group at the time. He learned our tools and partitioned the master, and the whole thing took a day. Another nice thing we were able to show is that when everything's expressed in queries, it becomes very easy to monitor the system because you simply query some of the subqueries and you get monitoring. So interposition of logic becomes very clean in this implementation. So many of the things we liked about it were sort of software engineering and systems benefits. And yet, not everything was rosy. And I should be somewhat honest here. Our language, it turned out, was kind of dodgy. It didn't really make sense as we discovered painfully over time. It turned out, and shame on me as the leader of this team, that very much like with Prolog, our language Overlog depended on understanding the interpreter we had built for Overlog. And when things would go weird, we would just hack the interpreter and change its behavior, hoping to get it to work. And then, of course, other programs in Overlog would break because we had changed the semantics of the language. So we would go back and forth between our specs and our interpreter, and we were in a hole. And the particular problem that happened would typically center around state update. So think of that as SQL table update, inserts, deletes, updates. And the uncertainty that comes up, naturally in distributed systems through the asynchrony of communication. So the interleaving of messages between nodes, as well as the reordering of messages across a channel, right? These were sort of causing us to tear our hair out. And the problem, fundamentally was that, as I showed you in that example of routing, we're pretending that there's a giant database in the sky, when in fact, there's one database at every node in the network, and they're communicating with each other asynchronously. And, it's classical in distributed databases that you need to do something about your distributed system to make sure that it makes sense, that it's consistent in some sense. And look, people have won Turing Awards for this stuff, right? So Leslie Lamport famously invented Paxos, which is the consensus problem. So the simple version of this is get a fixed set of machines to choose the same thing. That's what Paxos does. And then there's state machine replication, which is in the same paper essentially, which gets a fixed set of machines to choose the same thing in sequence, right? So you end up with essentially replicated state machines at every node, chunking out the same sequence of steps. So consensus is certainly very useful. In the database community, this is Jim Gray on the right, another Turing Award winner. We have transactions. Gray famously invented the theory and the early implementations of transactions. And here we're trying to get a fixed set of machines to agree to commit a transaction or not, depending on whether it can be serialized in a serializability schedule. And Gray actually didn't take credit for two-phase commit. It sort of emerged from the community, but he is the father of transactions. So we'll give him credit. The thing with these protocols is that they're pretty tricky. Every time I have to teach Paxos in particular, I really have to stop and go back and go over the protocol in detail to make sure that when I present it to my students, I don't confuse them and I don't get any details wrong. It's tricky stuff, and building it is extra tricky. And it's one of these unfortunate things that not only is it complicated, but probably you don't want to use it. All right, and it's funny, we have these sort of famous results, and researchers love to write papers refining this stuff, but actually in practice, you mostly try to avoid these protocols. And so let me quote from James Hamilton. You don't have to take my word on this. James is one of the architects of the cloud. He famously goes back to time at IBM and databases, time at Microsoft and operating systems. And then increasingly at Microsoft, he was doing warehouse scale computing. And then he went to AWS and was one of the architects of the modern cloud. And he gave this great talk that was reported on in 2009 at the Lattice workshop, which was the predecessor to ACM Symposium on Cloud Computing. And in the talk, he said, the first principle of successful scalability is to batter the consistency mechanisms, things like Paxos and two-phase commit, down to a minimum, make it as hard as possible for application developers to get permission to use them. And the reason he's so negative on these protocols is A, they're slow. These protocols force the system to stop and wait for a whole bunch of nodes to sort of vote on things. But that's not only the problem. The problem is that in any sort of distributed services environment, one system is inevitably waiting on another. So if you let some junior engineer put Paxos in the middle of a protocol, that person probably doesn't have the perspective that the ops team has, which is that there's 17 other services that depend on that service. And so while you're waiting for some node in the middle of the Paxos, in the middle of some subroutine, you would get queue backups across the entire cloud service from all kinds of things you didn't expect. And this is a nightmare to debug and to manage. And so, his general advice is, you almost never use this stuff. You only use it for background processes, and only the gurus should be doing this kind of programming. So in some sense, thank you, Dr. Lamport, for all the Paxos, but really we shouldn't use this stuff. In our experience, back at Berkeley doing our little research projects, we didn't need any of this coordination for network routing. We didn't need transactions. We didn't need consensus. We did, it turns out, need it for certain of the DHT overlays that were a little bit racy. The Symphony DHT in particular, I remember, caused us to start investigating these problems because it wasn't really working. And then we implemented Paxos as part of the file system work because that's how you do distributed file systems. You just do state machine replication. We just took it for granted that that's what we needed to do, so we implemented it in our language. But this sort of going down this progression, we were getting hotter and hotter, right? We were starting to do things that Hamilton says you shouldn't do, and so this led me to ask, when do we really need this sort of Lamport two-phase commit stuff? When must we coordinate, and when can we find something more clever where our programs can avoid the coordination? Which leads to a more fundamental sort of theoretical question, which is like, what is coordination really for? And nobody had ever asked this question. There are endless papers on these protocols, but the papers don't ask, like, fundamentally, when can you avoid coordination and when do you require it? The motivation is always circumstantial. If you have a race in your program, you can solve that race by using coordination. Okay, but maybe I can write the program in a different way and not have a race. Yeah. So is there a compiler or a clever programmer who can avoid the coordination entirely? Not a question people had asked. So today, the next step of this is, first let's clean up our language semantics, and I'll talk about that. So we had a language called Dedalus, which is a formal language, and then a sort of usable language called Bloom. And then this led to, the question I was just posing became the CALM conjecture and then the CALM theorem. So I'll talk through both of these. Dedalus is essentially data log with time and space. So it's data log for distributed systems, if you will. And it became the foundation for a series of papers, not just in my group, but in a bunch of theory groups for looking at communication as part of computability and complexity. So it's a nice formal model for talking about time and space that Peter Alvaro, my student, who's now at Santa Cruz, developed. And then Bloom is the language we built. It's a Ruby-based functional DSL. It's sort of based on Dedalus, although it has a functional veneer. And we extended it to incorporate not just logic programming, but also lattice types, which I'll talk about shortly. So Dedalus, is about time. One of the things you learn from Lamport and his work, I'm sort of, prodding him because he's a titan. So, he can take a little critique. But, the thing that he famously taught us is that distributed systems are not really about space. They're about time. It's about having different nodes have different perceptions of time. And so what we do in Dedalus is we're going to take data log and we're going to constrain it. So it's actually a specialized data log in which all predicates will have logical time as their rightmost attribute. And we're going to have restrictions on the rules that are going to track the state over time. Okay, so it's a data log variant. And there's this saying, time is what keeps everything from happening all at once. It's been attributed to a lot of people, but the earliest references in this sci-fi story from the 20s. And this is going to keep coming back to us. The problem with plain old data log is that inference sort of happens instantly, and we need to have a way to talk about things happening over time. Otherwise, we really can't talk about the things we do in distributed computing. So we'll see this. Here's the sugared version of Dedalus, which is maybe easier to look at. There's three kinds of rules that are allowed. There's plain old data log rules, which are sort of, think of them as being immediately evaluated. So if we have a fact in Q, AB, then we have a fact in PAB by deduction. And then we have what we call inductive rules, which are sequential, where we say if we have a fact Q in AB, then at the very next tick of the clock, and we'll talk about what that might mean, we have a fact PAB. All right, they're not coincident. They don't happen at the same time. Q is true at time t, P is true at time t plus 1. And this is precisely what I was talking about with time being the thing that prevents everything happening from all at once. Q and B can be contradictions, and that's okay because they're at different times. We'll also need to model distributed computing. So we'll have asynchronous rules where we say if we know a fact Q, AB, then at some time in the future, asynchronously, we'll know P, AB. All right, so this is the syntax sugar. Here's the actual data log for it. Right, deductive rules, the timestamp attribute, which is the rightmost attribute, was hidden previously. Now let's look at it, and let's just put in the logical predicates that make it right. Deductive rules, immediate deduction, S equals T. Inductive rules, S equals T plus 1. And then asynchronous rules, there's some time relation, S, which you can think of as an infinite set of integers. And then there's a predicate choose that takes a particular fact in Q and randomly, and a particular time S, and randomly chooses a time T. And this choose operator actually comes from the database theory literature. It has a lovely model theoretic semantic of what are called stable models. So this is Sakan Zaniolo down at, I guess he was at Texas then. Carlo's been at UCLA for a long time. And I won't have time to explain stable models in detail, but the idea is there's many possible worlds, right, in these programs. And what choose does is it creates all the possible worlds that are so-called stable. But you can think of it for now as kind of choosing a random time for every fact in Q. Okay, so in some sense, if data log is a relationship among facts, Dedalus is a relationship not only among facts, but amongst states of these facts, among states of the system. And it gives us this ability to have these key relationships we need for distributed systems captured in a logic language. We can capture sequentiality when we need it. All right, so if we need to talk about sequentiality, which is tough in distributed systems to achieve, we can say it in this logic. We can also talk about mutual exclusion in the spirit of this time keeping everything happening from all at once. We can say that two facts are not true at the same time. They're true at different times. And we can achieve things like atomicity by having a whole set of facts be declared to be true in the next time step. So that sequentiality, those inductive rules allow us to have atomic change to large sets of facts, because after all, data log is a set-oriented logic programming language, and we can have sets of deductions happen with the same time predicate. So the semantics for Dedalus, again, we want a model theoretic approach. This is sort of the roots of declarative programming and logic programming. Datalog famously, beautifully, has this unique minimal model, right? For every Datalog program, there's a assignment to the variables that satisfies the program that is minimal. And there's only one such assignment, right? So there's a clear consensus definition of what a Datalog program means. It's the unique minimal model. And even more lovely, it coincides with the least fixed point execution semantics. So the natural way to execute the program and the natural way to define the program are one. The really beautiful thing about Datalog. In Dedalus, we have some trouble. So now our facts are spread across time, and we might express facts like persistence. If we know a predicate P at time t, then it should be true at time t plus 1. That means predicate P persists, right? That's a frame rule, if you're familiar with that terminology. But what it means is that P is true across an infinite series of time steps, which in Datalog is considered an unsafe program. It has an answer set that's infinite. So we have to talk about minimality in some new way here, because all our programs become infinite in Dedalus, all the natural programs. The other issue, of course, is the choice construct, which gives us not one, but many possible interpretations of the program. And this non-determinism really makes uniqueness difficult to talk about too. So we don't have minimality, we don't have uniqueness. What do we have? And so we came up with an extension from stable models that we call ultimate models. And we've been through a couple of iterations of this in various places. I actually recommend the first technical report as a good place to start if you're interested in this stuff. But the basic idea with ultimate models is regardless of the choices that you make with the choice predicate, eventually all the messages get delivered, all right? At some finite point in the trace, there's no more messages to be delivered. And from then on, the facts that are eventually always true are called the ultimate model. There may be many ultimate models for a given program, but programs that have a unique ultimate model we'll consider to be Confluent programs. Okay, so this definition of ultimate models gives us a clear model theoretic interpretation of Dedalus. And there's a subset of Dedalus programs that are nice. They have a single, in some sense, a single minimal model in the spirit of Datalog. It's a single ultimate model. And those are the Confluent Dedalus programs. So having looked at the Dedalus language, let's return to my bigger question in some sense, which is suppose you understood your program semantics and you weren't just concerned about reads and writes or loads and stores. You wanted to ask the bigger question. I have a program, it has logic to it, it has semantics, it has a declaration. Is this program meaningful in a distributed system, right? So Lamport and transactions and all that are really all about read-write traces. But here I understand my program semantics. So given that I understand those semantics, which such programs have a coordination-free implementation? They're in the green circle. These are programs that some compiler or some creative programmer could find a coordination-free implementation that maintains the semantics of the program. So I want to know what's in the green circle. And then, of course, I want to know the complement. Which programs require coordination? These are the ones that are outside the green circle, right? And that green line there, that's the bright line that we want to define between programs that are coordination-free in their intrinsic sense and programs that simply require coordination. There's a question of computability. So I'm really not asking the circumstantial question of if you have a race, how do you fix it? Because the answer to that might be, well, there's a different implementation of your program that's in the green circle. Just go find it, right? So I'm not interested in solving races. I'm interested in asking the question of whether there's a way to build the program without races or where the races don't matter. And that's going to be very attractive for distributed systems. Coordination is really the big, it's the biggest rock in distributed computing. It's the thing that really messes us up. So I gave a keynote at the PODS conference about 11 years ago, 2010. The Declarative Imperative was the name of the talk. It's, the talk slides are full of inside jokes. The paper's a little bit less database centric, although it is still kind of podsy. But it's a series of conjectures based on our experience with routing and so on at that time. And the main conjecture in there, sort of the one from which we riff the other ones, is the CALM conjecture, consistency as logical monotonicity. And what the conjecture asserted was that a distributed program, P, has a consistent and coordination-free distributed implementation. It's in the green circle, if and only if it's monotonic. Okay, it seemed to me that those two things were the same. And I won't go into the intuition because instead we'll look at a proof that came the very following year from a graduate student at Hasselt University, Tom Amalut, and his advisors, who are serious PODS people. And they proved this. And in order to prove it, they had to take my sort of casual assertions and they had to put definitions behind the keywords: consistent, coordination, and monotonic. And so I'm going to step you through the intuition behind the proof of the CALM theorem next. And a lot of it, like a lot of logic programming research, depends on getting your definitions right. This is the signature of logic is syntax in some sense. So we really need definitions and syntax right. So we'll need formal definitions for these terms, and we'll take them one at a time. Consistency, we'll use our notion of confluence, which I introduced in Dedalus, to define consistency. Because remember, we want an application semantics notion of consistency. We don't want the sort of what systems people like to call eventual consistency or replica consistency, which is just a read-write model, because it loses the semantics of the program. Here we want an application level definition of consistency. And the way we'll do it is we'll say a distributed program is consistent if it's a deterministic function from a set of calls at the input. So think of these as API invocations or REST calls, to a set of responses at the output. So it's a deterministic function from sets to sets, and independent of its message ordering or any duplication of messages, it is deterministic. Okay, and so those messages might be the order of messages inbound to the system, or they might be the messages within the system that it uses to do the distributed computation. So independent of all that message ordering or duplication, program's consistent if it's a deterministic function. And our computational model here, again, we're going to need definitions. We need a definition of a program, and we have to talk about these sets of inputs and outputs. And so the model that Amalut and company used is actually an operational semantics. And I'd love to see, by the way, if someone's interested in this topic, a purely model theoretic proof of the CALM theorem would be nice. And I think all the pieces are in the literature, but they used an operational definition where they used what are called relational transducer networks. So in this picture, I've got a 4-node in the center of the slide, a 4-node distributed system. All the nodes can talk to each other, and a zoom out of one of the nodes. They all look the same. And the node is a relational transducer, which means it takes it at every tick of an event loop. It takes in an input set of messages. It inserts them into relations. It then uses a query language to define the program that's going to happen at each tick. And you can parameterize your relational transducer network with one or more query languages, which can have different levels of expressivity. And then based on that query, you compute the results of that query. Some of those are defined to be sent to the output, which either reappear at the very next step locally, and those are inductive rules, or appear at some other node in the transducer network at some point unknown randomly in the future, and those are the asynchronous rules. So it's very similar to a kind of operational semantics for Dedalus. So these relational transducer networks are key to the sort of the whole way these are constructed, these proofs. The definition of monotonicity in logic programming is totally straightforward. If you have a program P, input set S, input set T, that's a superset of S, then P is monotonic if P of S is a subset of P of T, right? Nice thing about logic programming is monotonicity is easily checked conservatively through a syntactic check, right? If you use a logic language like first order logic, existential quantifiers are monotone, universal quantifiers are non-monotone, totally syntactically obvious. If you prefer the relational algebra, cross product, selection, projection, join, all monotone. The only non-monotone operator in the algebra is set difference. I left out union. Union is monotone. There are cases, and we'll talk about this in a little bit, where you can find even more monotonicity than the green syntax. But as a conservative check, you can look for red syntax in a program and say, hey, you might have a problem because you're using a non-monotone declaration here. Okay, really nice. It's hard to pull that out of other languages, this notion of monotonicity. Now, finally, we have to define coordination. And this is where I think Tom was really brilliant, is in coming up with a definition. So think about this. We have a bunch of messages flying around in a distributed system. Which of those messages is intrinsic to the program? And which of those messages is coordination overhead? And how can we formalize that? And so the formalization they came up with, really quite nice, assume that the program starts with this input set T, okay? And that input set T starts by being, sprinkled through the network. It's partitioned in some way across the nodes of the network. And we'll say that a program P of T uses coordination if it requires messages to be sent under all possible input partitionings of T. And the one that I encourage you to think about first is there's a partitioning in which all of T is on a single node. If your program still has to communicate when all the data is in one place, Of course, it may not know that the data is in one place, but it happens to be in one place. That communication you're doing now is pure coordination. All the data flow of the program can be achieved on that one node, right? So anything else you're doing is just checking to make sure nobody else has anything else to say, right? It's coordination. So this is the definition they use of coordination, and it's really quite natural once you have it, but it sure wasn't natural to me at the time. So two canonical examples of distributed systems programs. These are literally from the canon. The first one is distributed deadlock detection, which comes out of the database literature. So the graph we're looking at here is a waits for graph on transactions holding locks. The boxes are machines, the circles are transactions in this top diagram. And machine 1 knows that T1 is waiting for T3 on a lock. And machine 2 knows that T3 is waiting for T1 on a lock. And once machine 1 talks to machine 2, together they know there's a deadlock. They know there's a cycle in this graph. They do not have to talk to machine 3 to determine that there's a deadlock, because it's a monotone program. Whatever machine 3 says will only lead us to find more cycles. It will not cause us to revise our output belief that there is a cycle between T1 and T3. Okay. By contrast, let's look at garbage collection, another pathfinding transitive closure graph problem in distributed systems. So we've distributed object model. We have our objects spread across the network in this lower diagram. There's some root object, and the objects have references to each other. Here, machine 1 and machine 2 talk to each other. Can they decide autonomously that 05 and 06 are garbage? No, they cannot, because there may be a path from root that goes through machine 3. This is a non-monotone program in the sense that machine 1 and machine 2, if that was all the data, they would decide that 05 and 06 are garbage. But there's the risk that new paths might be known in the network that would render 05 and 06 live. And so these two examples are so close. They're both just trying to find transitive edges in a graph. The first one, though, has got an existential predicate. It's very clearly monotone. The second one has a non-exists predicate. It's clearly non-monotone. So hopefully this gives you a flavor and intuition for why these problems are what they are, and sort of how nice it is to have this property that monotonicity is all we really have to look for to decide if there's a coordination-free implementation. So the CALM theorem, just to recap, a distributed program P has a consistent coordination-free distributed implementation if and only if it's monotonic. Original conjecture is in that Sigmod record paper. The journal version of the original PODS paper in 2011 was in JACM 2013. And then I'll allude to this in a couple of slides. The definition of monotonicity can be weakened. It can be broadened if you prefer. And there's a series of papers from a similar team with some folks at UC San Diego, Daniel Zinn, on that as well. We recap all this in this recent CACM article, which is for a general computing audience. So it's an easy read, 6 pages, if you want to start there. So, I alluded to this just now, this notion of weaker forms of monotonicity. Let me give you a flavor of this. These guys defined a notion of policy-aware transducers, which captures the way that a lot of distributed systems are built. Suppose that your distributed system knows how the data is partitioned. Very typical in a distributed database that we know that a table is partitioned by a particular column, and we know that there's, say, n nodes in the network, and that each row is at a hash function of its value in the partitioning column. And so we can answer what seem to be universal quantifiers, like, does there not exist a value, 4? We can answer that by asking the node responsible for 4. We don't actually have to ask everybody. And so in some sense, universal predicates on the partitioning columns become existential quantifiers on the node that has that value. And so they formalized this in a notion of policy-aware transducers, and they came up with different definitions of policies where you could have more or less knowledge of the policy. And that the more you know about the policy, the weaker your definition of monotonicity can be. There's more and more programs that become coordination-free. And this connects to the hierarchy of descriptive complexity, the different languages, the different declarative languages and their expressive powers. And so they have that in the paper as well. But an open question, which I'll come back to at the end of my talk, is what more can we say about practical notions of weak monotonicity that will allow us to unlock more coordination freeness in real systems? So this is, I think, a really exciting line of work that deserves more attention. So this is a long story. As I said, a good starting point might be our CACM paper, but it's very light. A better survey, although it's a little out of date, most of it's in there, is Tom wrote a Sigmod record paper where he covers a whole bunch of work, much of which I don't have time to talk about today, on things like decidability and language design and variations on Dedalus that have been used in tighter, more tightly coupled models. There's a whole bunch of stuff in Tom's paper. I encourage you to look there if you want to start digging into the theory literature in this space circa 2014. Okay, so this gives you a flavor of some of our logic foundations. I want to connect this to algebraic approaches, which are very natural and which have captured the imagination of at least some of the systems community in a way that's analogous to this CALM thinking. So my systems friends, they really don't like logic programming. It's really something and I relate to this. I hated it when I learned it in grad school. I had to take database theory at Wisconsin. Everybody at Wisconsin in the database group had to, there were 5 database professors at Wisconsin when I was there. So I really didn't like data log when I first learned it. And so I relate to these folks. I've learned to love it over time. But mostly they want to talk about stuff like reordering API calls. Look, Joe, all we care about is these black box API calls. Tell me which ones can be reordered in their execution. That's my notion of thinking about, order insensitivity in programs. And it's really a nice algebraic notion. Really, we're asking what's associative and commutative and idempotent. Here's a paper that I strongly encourage this community to read. It's called Building on Quicksand. It's many years back now, but Pat Helland sort of makes a point. He's sort of our representative in the database community of application developers and their design patterns, particularly for transactional business applications. And Pat, as long ago as 2009, was saying, look, folks, people don't use transactions in the real world. They turn them off. And here's what they do. And he had been working on things like Dynamo, if you know that, key value store at Amazon at that time. And a lot of clever techniques that focused around associativity, commutativity, and idempotence, which those guys dubbed ACID 2.0 in a nod to ACID transactions. The new way we get consistency is associativity, commutativity, idempotence. All right, so this is such simple stuff, right? This is joint semi-lattices. We don't have to make up a new name for it. There's a name in the literature. We're just adding D for entertainment value, right? So that's nice. Let's just stare at this for a second. If you take a kind of von Neumann approach to dealing with storing an integer, and you have a disorderly input stream, you will assign the value of the input stream to some variable over time. If you take if you like, ACID 2.0 or a lattice view of this, you need a associative, commutative, and idempotent operator to deal with every input. And the natural one on integers might be max or min. We'll go with max. And if you plot these things over time, the von Neumann thing is clearly non-monotone. The associative, commutative, idempotent thing is clearly monotone, right? It's very straightforward. And this is, which is familiar, right? This is the connection between this kind of algebraic view and the logic view. ACID 2.0, lattices are monotonic. This is a direct result of the semi-lattices, right? The semi-lattices define a partial order. And as you do join or least upper bound in a semi-lattice, it's not called least upper bound for nothing, you climb the lattice, right? And as we all understood, my systems friends as well, if things are commutative and associative and idempotent, clearly they're confluent, right? And so they're eventually consistent without coordination. So this algebraic approach, at least is the easy direction of the CALM theorem. It says, look, things that are monotone seem to be consistent. And here's a nice algebraic way to think about it, which is lattices. And in fact, Mark Shapiro and his team at INRIA sort of jammed on this quite a lot. So they defined what they call convergent replicated data types, CRDTs. And a CRDT is nothing more than an object-oriented semi-lattice class. So we have a class, it's got a merge function. The merge function is associative, commutative, and idempotent so that replicas of this data type can share updates in the background or share values in the background and keep each other lazily up to date. And the order in which they send these messages doesn't matter. But the really clever stuff in their work is, of course, their implementations of many handy data structures and applications as CRDTs. They show lots of stuff that's in the green circle, right? They show lots of things you can build in this design pattern. The problem is scoping this stuff because testing whether your application is a CRDT is pretty hard. These folks went pretty far. They built an entire collaborative editing system as a CRDT. So think of Google Docs. But now they have to answer the question, are the APIs to my implementation of Google Docs associative, commutative, and idempotent? And that on a big software base is hard to test. How can you be sure of that? And here's a tweet from just last month, or 2 months ago now, I guess. Martin Kleppmann, if you don't know him, is a well-known figure in distributed systems. He has an O'Reilly book on distributed systems. And he just recently posted how he wrote down a simple CRDT for class, 10 lines long, and then he found a fatal bug only after spending hours trying to prove it correct. Like, this stuff is tricky. You really want help from a compiler or something, right? You really want to test this stuff. So we started doing this in our Bloom language pretty early on. Our goal at least was to shrink the surface of things we had to prove down to something very small. So let's write simple lattices like sets with union or integers with max that are easy to test. And then we want to compose them together into larger programs. And this topic has come up again. I want to call out the work on DataFun. Michael Artsenius has a series of papers that very much are doing exactly what I'm going to describe in a more formal functional framework. Really neat work. But I do want to give a shout out to my students, and particularly Neil Conway, who were doing this some years earlier in Bloom. The idea with monotone functions is they're monotone maps from one lattice to another, right? You can take the set lattice, and cardinality is a monotone function on the set lattice that takes you to this int max lattice. And then a threshold predicate, like is the cardinality greater than 6, is a monotone function to the Boolean lattice, okay? So you can compose these very simple lattices into bigger things and start to build up program logic. And some of your lattices may also be morphisms, that is to say monotone functions that distribute across your merge operator, across least upper bound of your lattice. Why do we care about morphisms? Well, this allows us to do differential computing, or if you like, data flow, or really lattice flow, right? So we can do these delta-based query processing tricks that we know in databases and data flow, but we can do it on any kind of lattices. And then the techniques we know from databases port. So, differential execution, like semi-naive evaluation from databases, we implemented it in Bloom on all our lattices. And neatly, Michael Artsenius, his more recent paper, the 2016 paper, is a demonstration, theoretical proof that semi-naive and that applies to DataFun. So, this is very natural and very nice. And the DataFun stuff, puts it on a functional grounding, which is cool. Really like that. We've exploited this in our work in a bunch of ways, and I don't have a ton of time to talk about this, but we have a key value store we built in the last couple of years in my systems team called Anna. And Anna is a mutable state, key value store. So you can think of it as a register if you like. It's implemented in C++, but that C++ is a set of lattice implementations, each of which is very small. And then you can implement a wide variety of coordination-free consistency levels. This is another thing we did research on. That's this VLDB 2013 picture in the upper right. There's a set of familiar consistency definitions in the systems and databases literature that can be achieved without coordination. So this is read-write thinking, but it's read-write thinking with a weak notion of consistency. And we're able to implement all of them in Anna by encapsulating data with lattices. And Anna therefore runs without any coordination, which means no atomics, no locks, no distributed protocols. Every core on every machine is just doing puts and gets like 90% of the time, even under contended writes, even when everybody's hitting the same key and doing updates to the same key, everybody's just writing to that key and they're going full tilt. So this thing is crazy fast, even under contention. It's way, way faster than any other system out there in the literature, because all the other systems are at least doing multi-core atomics and retrying atomic instructions over and over. So lock freeness is not the answer here. The answer here is to truly, truly avoid coordinating. And then the thing is super scalable really smoothly across cores, across servers, across the globe. So Anna's a really cool systems delivery of these ideas of monotonic programming. Okay, so hopefully this gives you a flavor of both the logic and the algebraic approaches to avoiding coordination and building really scalable systems. I want to close with some open problems. The first few come from the CALM theorem still. The first one is the constructive version of CALM, also the relaxed version, which I'll talk about. So CALM says what's possible. It says there's things inside the green circle, monotonic programs, and things outside. But it doesn't help you take your current implementation, which is full of locks, and turn it into a coordination-free implementation, right? It doesn't help you achieve a coordination-free implementation. So it'd be really nice to have a constructive method to do this. Now, almost everything's undecidable, like most language problems. You folks know this better than me. But we'd like some help. And often we can get help even for undecidable things. So my input's a problem that, maybe is monotonic. I have an implementation that isn't, but the problem is, and I would like a coordination-free implementation, or at least some help designing that implementation. A fancier version of this is what I call relaxed CALM, whereas the input is truly non-monotonic. The expression of the program couldn't possibly be implemented without coordination. But most systems people in that scenario say, okay, look, I'm just going to implement it without coordination anyway and see what happens, right? So what I really want is a principled way to do this. I want a relaxed specification that is monotonic, but somehow it captures the spirit of the input program. So it does as little violence to the semantics of the original desired program, but it does give me a monotonic expression that I can then implement in a coordination-free fashion. This kind of direction would be super useful to programmers. And of course, I think it'd be really interesting in theory as well. Totally separate problem. Stochastic notions of CALM. So well-known paper from 2011 by my colleagues Ben Recht at Berkeley, Chris Ray at Stanford, and their then collaborators when they were at Wisconsin, Hogwild. And they showed that stochastic gradient descent, which is at the center of most optimization problems in modern machine learning, could be implemented on a tightly coupled but still parallel computer without any coordination. And their proofs, which required very quick messaging, so it was sort of customized to shared memory, but still very, very interesting, showed that, from a statistical perspective on expectation, you get to the same optimum regardless of whether you use coordination or not during stochastic gradient descent. And it's a very exciting paper. Some years later, one of Chris's students at Stanford, Chris Dessau, had a characterization of the problem that was really lovely because it began to smell like, or lovely to me, began to smell like CALM. It said, one way to look at this is through this notion of super martingales, which are stochastic processes where the expectations are monotonic over time, okay? And if you can characterize this stuff as super martingales, things start to smell like monotonicity checks. Now, no one's really sat down and said, how can we map this NeurIPS 15 paper to the CALM theorem and really what's going on at this juncture between logic and statistics? And how are we taking a statistical property and mapping it to a logical predicate? But we're close here, I think. So this is pretty exciting to me because we really do need to marry these fields of stochastic programming and logical programming. One of my favorite problems is this idea that maybe we can get lots of programs to be monotone, and it's been lurking in front of us this whole time. So classic result in descriptive complexity in logic programming is this Immermann-Vardy theorem. So to start, we need a definition. Semi-positive data log is data log enhanced with negation, but only negation on stored facts. So you can't negate derived predicates. You can only negate stored predicates. But the key here is there's also a successor relation. Okay, so you have access in your programs to be able to say a successor predicate in the right-hand sides of your rules. And the Immermann-Vardy theorem, which was independently proved by Immermann and Vardy, Vardy 4 years earlier. So I think it's always been very nice of Moshe to share this as the Immermann-Vardy theorem. But it shows that semi-positive data log can express all of PTIME exactly. So those are equivalent characterizations of a class of programs. Well, let's face it, in distributed systems, we don't want to run exponential numbers of steps over a network. So PTIME, man, if we could get all of that, we'd be golden. So my question is there a practical weak form of monotonicity that corresponds to semi-positive data log? Very much the way we talked about policy-aware transducers. Is there some sort of semi-positive transducer? To do this, we need a successor relation. We need a source of order. And if that source of order is multipaxos, we've lost, right? The whole point was to try to avoid an ordering protocol and to somehow pull order out of the configuration of the system. And Immermann argues in his book on descriptive complexity that order's right there in our computer. We have an ordered memory bank. We have a processor that operates in order. Order is like fundamental. There's always order available to us in the universe. Distributed systems, maybe that's just not true. But maybe there's clever scenarios, at least in some computing environments, where the order is there for us for the taking, in which case the CALM theorem should apply to all, the green circle is all polynomial time computation. In essence, everything should be computable without coordination. We really can follow James Hamilton's advice and avoid all that coordination stuff. So I think that's super exciting to try to figure out. I'll spend my last few minutes talking about the future work we're looking at in our group at Berkeley. I'm so excited to have Alvin Chung and Natasha Crooks having joined the faculty. Alvin, you may know well from his work on program synthesis. Natasha just finished a PhD at Cornell in distributed systems and distributed consistency, and has some foundational results in transaction semantics. And then Matthew Milano's joined us. He was a student of Andrew Myers at Cornell, so he brings a very similar background on monotonic programming from his research to our group. And Matthew's the one of the three of us who's going to be on the job market in a year or two, so pay attention to that, young man. What we're proposing is that cloud programming should be what we call PACT programming. There's an acronym that stands for separating out 4 independent facets of a program. The semantics, P, the program semantics, that's the functionality you want your program to have modulo distribution. So ignore distributed systems for a minute. Just write down for me, preferably in a nice, clean, declarative way, what is it that your program means? Then separately, let's worry about distributed systems problems. First, availability. What do you want to be the availability of the APIs of your program? For each API, how many failures can it tolerate? Across what failure boundaries? Then let's talk about this notion of consistency. Maybe I'm willing to weaken my program semantics in the way I was alluding to previously on sort of this weakening of CALM, to say, I don't need perfect program consistency. Actually, it'll be okay if certain variables only maintain loose invariance on only maybe parts of my state of my program need to be consistent. And then finally, of course, there's the usual optimization problems, but in the cloud, there are almost certainly multi-objective optimizations that trade off things like latency against dollars spent on Amazon, right? And so we need a Pareto optimal framework for compilation, and we need it to be dynamic. We need this to generate not just .exes, to use Windows terminology. We need it to generate self-modifying deployments of distributed systems that will change their deployment and perhaps even their behavior based on workload. Right? So these have to be self-adaptive sort of optimization targets. Now, it'd be cool to just do all this in Bloom. When we were in the Bloom group, we used to carry around this XKCD. If you learned to speak Logiband, your communication would be completely unambiguous and logical, to which our systems friends would respond, yeah, but it would all be with the kind of people who learn Logiband. So this may be my first day hanging out with a whole bunch of Logiband people since at my last Datalog conference. But doing this in Bloom is certainly going to find resistance. So I'm leaning on Alvin's work on verified lifting here. Alvin's had this series of successes in lifting legacy code, like Fortran code, into high-level declarative programs and then compiling it back down to highly efficient vectorized and parallelized execution. He's done this for Fortran, compiling it to Halide, and Adobe Photoshop and others have used this to take dusty decks of Fortran code and vectorize them. And Alvin's done it for object relational mapping style programs with SQL and with Spark as well, to turn for loops into SQL queries that can then be re-optimized by an optimizer. So the hope here is that we can carry programmers from where they are today using verified lifting to a bloomier world of tomorrow with PACT programming. So we're building a stack we call Hydro, which is going to take a polyglot set of possible programming styles, sequential code, but also sort of the bare bones distributed frameworks that people use today, like futures and promises, actors, maybe functional reactive programming, and bring them all into a single internal representation that's high level. So think of an IR, but a declarative language IR, kind of like Dedalus. So we're calling that IR hydrologic, and it's in a PACT programming style, and then compile that down to a data flow language that combines data as well as lattice flow, the way I alluded to, and functional reactive sort of event flow. Put all those things together so that we can kind of capture all of these design patterns. And then it's got to be auto deploying, as I described, possibly calling out to existing frameworks. So we're really trying to make this whole picture, the theory that we did over the years, as well as the practice that we've done recently, and bring it together into a real compiler stack. This work has gone on for years, and there's way too many people for me to read out their names who've helped along the way. Some of this is just simply their work, and I'm just telling you about it. I want to particularly call out the key student PhD dissertations that came where there's multiple papers from each of these people that led to this work. Most notably, Peter Alvaro, who's the father of Dedalus, and Tom Amalut, who did all the theory really around the CALM theorem, all the proofs. and these other folks who did systems work that gave us the confidence to go forward. All right, I'll leave you with this. There's the CACM paper. We have this paper on Hydro looking forward, and then a GitHub repo. If you want to read something very light and share it with your non-technical friends, I have a blog post recently about serverless, and this all comes out of the Data Systems and Foundations group at Berkeley. With that, I'll thank you.
All right, thanks, Joe. So I think we have technically hit the break part of the program, but we'll do some Q&A here. And I think, Joe, if you're available for the next 15 minutes or so, we can stick around here for any overflow questions as well. I'll start by reading a question that Phil Wadler posed in the text chat. It said, "Thank you for a great keynote. We had another great keynote on Wednesday from Rashid." I don't remember how to pronounce his last name, starts with G. In it, he claimed that Bitcoin does not require consensus, even though that is how Nakamoto and others have implemented it. Can we draw a line from his talk to yours? Is Bitcoin calm, monotonic, and hence coordination free?
What a lovely question. I wish that I had the answer off the top of my head. I think that's one of those questions that merits some investigation. But I mean, what the CALM theorem is saying is that if the assertion is true that was made on Wednesday, then yes, indeed, it's got to be monotonic. Right, and at least for some definition of monotonic that accommodates policy or what have you, right? So it's really not a question for me. I think that was a question for the community, which is super. Which is to say, I don't know the answer. That's a
fair
off
point.
The top of my head.
We also have Matthew's response in the text chat for anyone who wants to see a second opinion. All right, so while we're waiting for any other questions to be posted in the text chat, I'll ask one of mine, which is that you cited a paper by a person you said was kind of representing the business users of databases for a certain kind of workload that you'd see in database textbooks in the year 2000 or whatever. Is the progression of tools you told us about applicable to that kind of example too? It seemed like you were choosing pretty different kinds of computations than like typical web application or a bank or something like that.
Yeah, so the examples in that paper were absolutely the examples we used in our first papers on Bloom. And so there were some very direct mappings. You know, the famous example is the one from the Amazon Dynamo paper of a shopping cart. The idea that we have replicated state of a shopping cart, you just add, you mark things that you want to add to the cart, you mark things that you want to delete to the cart, those become two sets. The sets are growing monotonically of adds and deletes. And that the Amazon Dynamo systems paper, the clever bits are not the system. The system's incredibly simple, and the application's been expressed in a monotone way. And that's one of the lessons of that paper, building on quicksand. Excuse me. And in our Bloom paper, we show how we can analyze a shopping cart program and prove that it's correct with the compiler by looking for that monotonicity.
Cool.
I should say that there's more in that building a quicksand paper. There's more agenda that we haven't addressed there, including a notion of memories, guesses, and apologies. So if your program goes wrong, say you can't deliver a product to a customer because it's out of stock, you don't do a functional inverse of their thing. You might send them a coupon. So there's additional logic in your program to compensation logic for things when they are inconsistent with spec. And that exception handling logic is one of the things that would be nice to have a formalism for that program proposes, sorry, that paper proposes, and the community doesn't have formalisms for today. When is exception handling logic sort of in some sense correct?
All right. It looks like we're getting more follow-on comments answering Phil's question, but not posing a new one in the chat. Okay, here's a question from Ryan Dungiz, or some pronunciation like that. Is there semantics for Dedalus programs that has something to say about executions, including message loss or other kinds of faults? He wonders if he's misunderstanding the notion of ultimate model.
Great question. So, you know, generally in the papers, we've assumed that what message loss is message delay. It's just, you know, unbounded delay. But someday, maybe, you know, that message will arrive, and then you'll have an ultimate model. If you really want to deal with message loss in a practical way, which is to say you want to deal with putting bounds on delay, like timeouts, right? Now you need a semantics that will tolerate partial outputs. For monotonic programs, you know you've got a subset of the final output. So that's something you know. But you know, if you have a non-deterministic declaration that we're just going to quit now. So the semantics become not well defined, and you're much more in this world of, or you're much more in a scenario of many possible worlds based on all the subsets of the possible output. So monotonicity, gives you a handle on how bad could my early returns be, right? If I stop the program early, or if I have a true infinite message, but they don't really give you a uniform semantics. And one of the pieces of this that comes up very clearly in traditional programming is if you read a lattice, if you have read is non-monotonic, you're actually not allowed to peek at the content of your lattice. You can only wait for it to hit top. Right, which is why you want monotone functions to the Booleans. You want thresholds so that you can get to a lattice that's actually at top, it's saturated, and now you know that for now and forever it's going to be at a particular value. But you can't really read from a lattice or from a monotone program until it's done. Otherwise, you have a subset.
Okay, so I have another question, which is, have you considered how these kind of mechanisms work in settings with various security and privacy concerns, where, for instance, some tuples in your database should be kept away from some nodes, or some nodes might be just plain malicious and sending random garbage?
I have not thought about that. I think it's very interesting. I don't know how that connects to this theory. That's a great question.
So it's a distributed system, but with kind of centralized control and trust.
So I would say it's universal trust in our model.
Okay.
We haven't worried about it. Now, having said that, I mean, if all we care about is data placement, then we're fine. I mean, that's an efficiency issue, right? Your data is not allowed to go certain places. Then you have to push the computation to where the data lives, possibly do it in enclaves or using homomorphic encryption. Things will slow down, right? There's nothing in the model that prevents that. But asking sort of a different question of what information needs to go where to compute what in these kind of monotone settings, maybe there's a fun research problem there. I'm not sure.
There could be cases where the data placement is itself sensitive information, if there's some derived facts that go someplace because someone belongs to a group or something.
Indeed. And some of this work on homomorphic encryption and enclaves is trying to address those kind of access pattern questions, right? Yeah.
Adam, I'd like to interrupt very briefly with two quick things, if you don't mind. I'm sorry.
Go for it.
So the first thing is I'm going to stop recording this shortly. We can record a few more questions, but then we'll switch to a sort of a more informal Q&A. And second is an email that should have just gone out to all POPL registrants, but because I have your attention now, I think I should repeat it here out loud. We're doing a small poster session for people whose talks were interrupted in the Wednesday service outage. So that is happening from 2030 to 2100 Central European time today. That is to say, after the farewell reception. So please go to the papers for those talks scheduled for the Wednesday outage and discuss in breakout rooms there so that you can meet with those authors and talk about their excellent work. And we are sorry again for all of the service difficulties. Okay, I'll record a few more questions here, and by the 15-minute mark, I'll stop recording, and Joe, you'll be host and you can continue. Sound good? All right, sorry to interrupt.
Problem. All right, let's see if our set of questions has reached a fixed point. I don't see any left in the chat that we didn't already get to. Does anyone want to pose anything else?
With a hand up.
Oh, okay. I always forget to check that. Okay, yeah, Leonard, you can try asking by voice if you're brave like that.
I was wondering whether there is a quantitative version of the CALM theorem, sort of where you sort of minimize instead of the number of communications needed, and thus perhaps a connection to communication complexity.
Lovely. So Paris Koutras, who's at Wisconsin now, in his PhD work with Dan Susiu, looked at complexity through the lens of how many rounds of coordination do you have to do to solve certain problems. And they were mostly focused on kind of query processing problems on big data. So, how many rounds of coordination is required to do different things, joins and other calculations. And so I would go there for sort of next steps on that. And they were using Dedalus as their formalism for doing those proofs. So Dan Susiu and Paris Koutras would be a good place to start looking.
Thanks.
All right, anyone else want to use that exciting raise hand button? I can try one more question of mine, sorry, Michael, which is, I wonder in practice, Joe, what advice you have for when people should use this kind of database solution versus a traditional one you can run on one beefy server with a simpler consistency model. I get the impression a lot of engineers get overexcited and plan for the massive scaling that most of them won't be lucky enough to experience and go for the harder programming model from the beginning. Do I have any kind of the right sense of that?
Oh, absolutely. I mean, from a practical perspective, you should just write your application in an ORM on top of Postgres, right? Until a further notice, which is roughly what Twitter did, and then famously had to scrap it and scale it and build their own stuff. But even at the scale of a rack or even a data center, transactions can be quite fast, and consensus can be quite fast, and it's eminently practical. It's really globally distributed systems. And in that, I include all the work on edge computing and fog computing and what have you, where you have shifting populations of nodes where you need to worry about this. And then the other thing I'll bring up is serverless computing, where the population of function invocations grows and shrinks with workload. These problems come up again because I didn't have time to talk about this, but one of the lovely results in Amelut's proof is that there's an equivalent third definition to monotonicity and coordination freeness, which is obliviousness, nodes that don't know the population and they don't even know their own identity. The monotone programs can be oblivious, which means that you can have fleets of invocations that come and go in a monotone program, not knowing what the membership is of the system, and it'll all work, which is super cool and very applicable to even serverless computing, which you might want to do on a small scale. So you can ramp up and down your population without doing membership protocols, which are a consensus problem.
Okay, thanks. So we might be at that fixed point now. I'll wait about 10 seconds for any last questions to pop into the Zoom chat or raise hand buttons to appear.